Hi, we are going to be looking at analyzing the concentric cylinders experiment. We're not going to do complete analysis, we're just going to get you started. So what I have here is a set of data. The first thing that you want to do, of course, is construct a graph. Always make the marker-only scatter graph. Let's make it a little large so we can see. I'm going to select my data. Add the X series values. I'm going to add my Y values. And what I see is that it's not linear. Okay? So you're going to add a trend. We're going to display the equation, display the R squared, and you can see the default is linear. It's definitely not linear. What you are to do is you are to move around and try different ones to see which one you think it is. Okay. I'm going to tell you flat out, it is not the polynomial. Okay. Yes, you can make it the polynomial fit. You can make a polynomial fit anything if you make it a high enough order. Okay. But we're going to go back to the trend line. And you're going to change it. Now, not only are you going to be looking at what is the R squared, you're actually going to be looking at what looks like it fits the best. Okay. Once you have decided on one, you're going to leave it and it's going to be set. I'm going to delete the trend line for now, however, because I didn't want to show you which one it was. Okay. Now, the electric field. This is going to be in volts per millimeter. What we're going to do is we're going to assume that the electric field for a small range of values is approximately the same as the average value on either side of it. So let's say I want the electric field for this point, 26.3 there. I'm going to assume that the electric field at this point is equal to negative. It's negative because remember that the relationship between E and V is negative. V is negative, the integral E dot dl. I'm going to bracket the point. I'm going to look at the point on either side of it. To get a value. And so this is the average electric field between 28 and 24 millimeters. We're going to assume that that average value is the same as the instantaneous value at 26. We'll see if that's good or not. I'm going to extend it up, and I'm going to extend it down. Please notice the top and bottom cells are blank. I cannot get my electric field for those values. And I'm going to set them also the same position. Okay. Now I'm going to construct a second graph. By the way, you need to put axes labels and chart titles and all of that. Clean your graphs up. Construct a second graph. This one is going to be for the electric field. Select your data, X values. The Y values will be your electric field. Because I started at 16, I have to include the blank cell in this data range. If you don't, what will happen is it will shift the data. You'll note that this graph is, again, very noisy. There's a lot of scatter in the data points. We are going to add a trend line. Defaults to linear, you can, oops, not what I wanted to do. I wanted to move this. You can tell that it defaults to linear. Okay. Again, we can change that format trend line. Change it to exponential, logarithmic, polynomial, power, moving average. It's not moving average. You have to decide which one it is. I will tell you right now again, it is not polynomial. I can make this do whatever I want by making the order large enough. So it is not polynomial. Pick which of the other ones it is. Okay. Again, you're going to do this by looking at the R squared and also looking at the actual fit of the data. It's not exponential either. Okay. Once you have done that, we need to make our graphs linear so we can do a regression. So I'm going to put a trend line back in here. I'm going to put the wrong trend. I'm going to tell you flat out I'm putting the wrong trend in. Okay. I'm selecting a power trend. It is not a power trend. Sorry. I selected polynomial trend. It is not the polynomial trend. In order to make this graph linear, what I would need is I would need to have take this function. So what I would have, I like to call it f of r. And you're going to type f of r is equal to e to the r, log r, r squared, r cubed, whatever it happens to be. Okay. Let's say this had been r cubed to make it a power. I need to make this larger so I can actually see it. The font's just a little too small for my eyes. It says minus 1.8. So I'm going to round this to r to the negative 2. Remember, this is not the correct one. So I'm going to take r and raise it to the negative 2. Copy it down. Now, when I make a graph, I want to make this graph so that this function is linear. I'm going to select my data. My x values will now be this f of r function. My y values will be my potentials again. Okay. The graph's not linear. I obviously picked the wrong function. This graph, if I have the right function f of r, should be linear. What I'm doing now is simply maybe making it hopefully a little bit linear, closer to linear. Still not the right function. Cannot stress that enough. This is not the right function. Okay, you're going to do the same thing for the electric field function, whatever this graph happened to be. And then you're going to make a fourth graph. So this is graph 1. This is graph 2. This graph, graph 3, this should be the linear graph. That's not what I wanted. Select data, edit, function graph. Okay. So this graph, again, this should be linear. It is not the right power or the right function. Once you have these graphs and they are linear, you can now go through and do a regression to get the uncertainties in the two linear graphs. I'm not going to show you any more of the analysis. We'll let you give it a try. If you have questions, contact your lab instructor, either during their virtual office hours or via email.